All right, this is the second class for manufacturing process, ME3221, Department of Leather Engineering, third year, second term. And in the first class, we have studied basically the introductory class it was, and we have just discussed what were the course contents and what we are going to study uh, in my part of this course. In my part, I'm going to talk about the casting and welding and allied processes. So today we are going to formally start our class using our course content, starting with casting. And today we're going to study casting along with how sand casting is done, how can we do the sand casting, and there are some basic terms used in casting process, and there are some components which are essential components of casting, casting method, and at the end we're going to talk about pattern, the pattern that is required for casting. So you'll get a good overview of casting as well as pattern and the sand casting, which is a very conventional type of casting. That means for manufacturing various kind of products. Almost anything can be manufactured uh, using sand casting. So what is casting? Casting is manufacturing a product. For casting, what we need is that we need a pattern. Pattern means the product that we want to produce. For example, I want to produce a mobile casing, okay, the mobile cover, whatever I say, the mobile. For example, we say mobile cover. Then I need to make a mobile cover using a different material, and then using that different material, we make a cavity of the same shape that we want to produce. Okay, and that cavity, in that cavity we pour the molten metal. If we want to make the casing metallic casing, for example aluminum casing, then we pour the molten aluminum into that cavity to and allow it to solidify for some time so that we can uh, uh, take out the solid part from the mold, and that is what it's called casting. Okay, that means in the formal definition we can say like it is a process of pouring molten metal into a mold. Mold means the cavity, the whole system including the cavity, into a mold in a cavity of the shape to be made, the shape, whatever shape we want to make, shape to be made, and allowing it to solidify for some time. Okay, and since it is done in the foundry shop, the shop or workshop where the casting is done is normally called foundry shop, and the another name for casting is also founding. Okay, it can be casting or it can be founding. And another important thing you need to know is that the casting, the name casting, the process of manufacturing something using the pouring molten metal into a mold of, in a cavity, the whole process is called casting. And also the product that you have found after casting uh, is sometimes also called casting. Okay, so don't be confused with that. The casting itself is a process and casting is a part that you have manufactured. And this process will be more clear once we go to the figure in the next slide, where there are many components of a casting will be shown, and there are some basic parameters that involved with casting. We will also discuss that. And before going to that, for conducting a successful casting or successful casting process, or to produce a part using casting process, we need to have some, there are some basic requirements for casting. First, we need a pattern. Whatever product we want to make using casting process, we need to have similar shape and size available to conduct the casting. That is what called a pattern. The pattern is a replica of the shape to be made. The shape or the product that we want to make, we need to make a replica of that, either using wood or plastics or even metal, whatever you want. you need to make that part first. You need to have a part, and then using that part, that replica, you produce a lot of parts. Okay, that's what the benefit of casting. Okay, so first we need a pattern, which is the replica of the final shape that we want to manufacture. And the second is the melting process. We need to have a melting process. Since we are talking about the metallic parts, then or any other parts during in the casting, the basic thing about casting is that you need to have a molten metal or molten plastic or molten material which will flow through into the cavity. Okay, the whole cavity will be filled up with the molten metal. So you need to have a melting system where you melt the metals or any other plastics or any other material, whichever you want to make, whichever material you want to use to manufacture a part. And the third one is the pouring system. How do you pour that molten metal into the cavity? Okay, so that's also important, because pouring involves, you need to be really careful when you are pouring molten material into the cavity. Okay, so sometimes you don't have to, because it depends on the what sort of casting you are doing. For example, if you want to do sand casting, then you need to be really careful during the pouring. You need to develop a pouring system. And also in the case of plastic parts, if you want to do casting on the plastic parts, then you also need to have be really careful where the gates will be, where how you introduce the molten material into the cavity. Okay, so you need to have a pouring system, how the molten material will be flowed into the cavity. And the fourth one is the solidification. You need to apply proper solidification method. In the case of sand casting, it is usually you pour the molten material and keep it there. Okay, keep it there for some time, so that the material gets solidified, and then you break the mold to take out the part. That is the solidification. And sometimes for the plastic castings, uh, if you want to do it faster, then because the metal cooling of metal takes a certain amount of time. If you want to make it faster, then you need to introduce another cooling system, okay, around the cavity. For example, um, let's say this is a mold, okay, a rectangular box. This is a mold, and this is the cavity. Okay, this is the cavity where you are pouring molten material through this way. This way, the molten material is being poured. Okay, the molten metal is being poured through this way, and this cavity is filled up, and then you keep it for some time uh, to get the heats released from the part, and then the part becomes solidified. Okay, and if you want to make it faster, uh, not like natural cooling, then you might want to introduce some holes in here, so that the water can be circulated, cooling water or cooling medium or air can be circulated through the holes around the part. Okay, so that you can make the casting faster. That means cooling time will be reduced, and you can take the part out, then the production capacity will be increased. Okay, so the solidification method also important in the case of casting. So the all the water cooling or air cooling sometimes may not be able to, you will not be able to introduce the faster process, even if you want to do it faster. But in some cases there are some limitations. Once you know all the casting processes, then you will be able to understand which one you could introduce extra cooling system, which one in which case you cannot. Okay, so after the study of all the casting processes, then you will be able to identify that. Okay, so we need the solidification method. Okay, it could be quicker, or it could be natural cooling. And the fifth one is the mold removal. You produced the casting, you poured the molten metal into the cavity, and then cavity has been solidified, the part is produced, and then how do we remove the mold? How do you take the part out? Okay, then you need to have the mold removal process. That means you need to have some sort of facilities, so that you can remove the casting part that you have just produced. Okay, so there are several methods for removal of casting parts. For die casting, there are ejector pins, And for sand casting, you just break the mold and take out the material, take out the final part. And in some other cases, you can use the vibratory shaker. Using the vibration, you can break the outside mold, but the internal part will be intact. So there are many other methods you can use for the mold removal. And the final one is the clearing and finishing. Okay, for clearing and finishing, you produce the part. Okay, the final part is produced, and then when you break the mold, then the metal will also be in this part. The hole through which you pour the molten metal, that one also will contain the molten material. That means the material. Okay, then once you get the final part, let me clear it. Okay, so this will be your final part. Okay, so once you get the final part out of the mold, this is your final part. Then you need to do some clearing and finishing. If you want to have the proper finishing on the surface, you want to coat the surface with some other materials, or if there is any defect on the surface, then you want to remove that. That is called finishing. Okay, and clearing means this is not the essential part of component of your part. You just need this portion. Okay, you just need the portion which uh, with the green boundary. Okay, just need this part, and that one is extra because of the casting process. You cannot get rid of that, and that is why after removal, after mold removal, you need to cut it off in here. Then you will get the final part. Okay, and that is called the clearing and finishing. So these are the 6 basic requirements of casting, or 6 basic steps, you can also say. Like a pattern, you need a pattern for producing a part, you need the similar type of part, similar part, a replica of the part you want to make, you need a melting process, you need a pouring process, you need need to allow the solidification, you need the proper solidification method. Sometimes if you want to do the solidification quickly, then you will have several defects into the casting. So you need to really justify it, which solidification method you should use. And then the mold removal, how do you remove the mold? You can use the vibration to break the mold. You can, for the sand casting, you just remove the sands. And for die casting or plastic product producing, you can use ejector pins for mold removal. And finally, the clearing and finishing. Clearing means you take the extra parts that are not necessary for the final product, you take them off by cutting, and then you can apply the finishing. For if you want better surface finish, then you can do more finishing. Sometimes in some advanced casting method, you don't need to do the finishing. It actually provides a excellent surface finish. Okay, all right. Do you have any question so far?
Sir, why sir melting is positioned in 2 but not in 3?
It's not these are the basic requirements. These are not the steps like you're following the steps step by step. Okay,
Okay, sir. Thank you, sir.
it's not a flow chart. All right,
Okay, sir.
these are the individual components you need, or individual methods you need. Okay, okay, any other question? Okay, so we are moving forward. So we are studying casting, but what are the advantages? First one, the molten material can flow into very small section so that intricate shapes can be made. The cavity, what we have been talking about in the previous slide. um, we have a mold. Okay, this is a mold. The whole system is called mold, and this is the cavity. Okay, this is the cavity where you pour the molten metals. Okay, whatever the cavity shape is, as we know that liquid can take any shape you provide. Do you remember that theory? Liquid and gases can flow, can take the
I
shape.
remember
Yes,
that.
sir.
You,
Yes, sir.
okay, then if the shape is very integrated, for example, if the surfaces are like very tiny surfaces in here, very tiny surfaces in here, then the liquid can flow very easily in those parts. Okay, and
So
that is why this is one of the advantage of the casting. Okay, please go ahead. Hey, someone want to ask a question? All right. So the very integrated shapes can be made because of the flowability of molten material. Okay, because the flowability of molten material can flow any places in the shape, unless it is very tiny, like uh, fraction of micrometer. Okay, so it will not be because of the viscosity, and material will not be able to flow in those cases. Okay, unless you can also apply the pressures so that the material can flow into those places too. Okay, so it is very possible, very much possible to produce integrated shape up to a certain limit. There is always a limit. And the second one is any material can be cast: ferrous, non-ferrous, plastics. Okay, whichever you can melt, you can cast it. The material that you can melt, you can cast it. Okay, that is the one of the advantages. Necessary tools are simple and inexpensive. This is not always true. There are some advanced casting methods where you need to have like specialized equipments. In that case, that might be expensive, but in terms of final product that you need, the value of the final product, that you can also say it is inexpensive. The method would be inexpensive. Okay. Size and weight is not a limitation. Okay. Whatever the size, you can produce that. Okay, it can be very small and it can be very large. For example, if you want to talk about the engine casing, okay, whatever the engine you see, like for example in the shallow machines, or the big pulverizer, where you see there are some machines, heavyweight machines, those casings are made using the casting method. Okay, even if a motorcycle engine is also made of or a truck engine is engine casing. Okay, engine body is made by casting. Okay, so whatever the size, it's not a limitation. The size and weight is not a limitation. You can produce a lot of products. And the better dimensional accuracy, surface finish also depends on the manufacturing method. If you are using the sand casting, you will not be able to get a better surface dimensional accuracy or surface finish, but also it depends on the experience of the workers who produces those castings a lot, and then they can get really good dimensional accuracy can be obtained using sand casting. And there are some other advanced casting methods where dimensional accuracy is not a problem, and also the surface finish is not a problem. But in the case of sand casting, you might need to do extra work on the finishing. Okay, and there is also disadvantages of casting. First one, labor intensive process. You might need a lot of labor, or you might need a lot of floor spaces for that. Okay, and the dimensional accuracy and surface finish is not good in the case of sand casting. That's what I said. Like better dimensional accuracy is not always true. Okay, in the case of sand casting, it might be different. Okay. Okay, that is the advantages and disadvantages of casting. These are not actually limited. There are so many you'll be able to see throughout the lecture. Okay, so not only this lecture, the following lectures will be, you'll be able to know a lot of advantages and disadvantages of the casting based on the various casting methods. Okay, so do you have any question in here for advantages and disadvantages? All right. So this is the component of a mold, that the mold that we have been talking about in the first slide. What is the mold? A mold actually consists of, these are the components a mold consists of. Okay, a mold has two important parts. One is together, both two of those parts actually together called flax. The whole system, whole sand, the casting part, the core, everything is contained in between two boxes. Okay, those boxes together is called flax. Okay, and the boxes where the boxes meet. Okay, this is the plane where the boxes meet. This plane throughout the whole casting, this plane is called the parting line. The top box is called cope. Okay, the top side from the parting line, the top part is called cope, and the bottom part is called drag. Okay, bottom part is called drag. So it is basically a empty container. The both sides are open. Okay, a container which in which the both sides are open, just a rectangular container. Okay, and this is called flux, and the container has two parts. The upper part is called cope and the lower part is called drag. Okay, and the middle part, that means the middle plane where the upper part and lower part meets, that plane is called parting line. And now, what are these? These are basically sand, because we are talking about this as a sand mold. Okay, the mold that is made of sand. These are the actually sands. Okay, the sands, using sands we produce the mold. Okay, and first I will go to that, how we produce the cavity and how we put the molten material into that. Before that, we need to know the various components of a mold. Okay, that's why this slide is all about. And in this case, uh, first I will go through the pouring system. Okay, for the pouring system you need to have a funnel like structure. Otherwise, if you pour the molten material, then it might spill on the surface of the mold. Okay, and that is why you need to produce a funnel like structure on the sand by removing the sands from this flat surface. Okay, it's a funnel like structure where you put the molten material. Okay, and that's called the pouring cup. Okay, and after the pouring cup, the hole through which the molten material penetrates into the cavity, okay, that is called sprue. Just these are the names given by the casting authorities. Okay, from the pouring cup, material flows to the sprue, and then material stays into the runner. This portion is called runner. Okay, okay, this portion is called runner, through which the molten material flows into the cavity, and the place where the molten material enters into the cavity is called gate. Okay, just before the cavity, that place is called gate. Okay, from the pouring curve, goes through the sprue, and then runner, and then goes through the gate, gets into the cavity. Okay, okay, the next, this is the ladder. You take the molten material from the furnace, and then you put the molten material into the cavity. Okay, and now there is another important part that is called open riser. Okay, this is usually called riser. The main purpose of the riser, there are two main purposes of the riser. First one is that when you pour the molten material through this way, if this region is blocked using the sand, then what would happen with the air inside the cavity? Can anyone say? Is there any way that air can get out of the cavity? Anybody listening?
Yes, sir. Listen, sir. The question is again, sir.
Uh, if this portion is blocked and there is a cavity, molten material is coming this way, what will happen with the air inside? We need to have some means so that air can get out. Otherwise, air will be trapped inside. Then the cavity cannot be filled with liquid metal, right?
Yes, sir.
That is why we need to have an open riser. Okay, we need to have a riser so that molten material comes through this way, it fills up the cavity, and then
The air is out.
air gets out through the open riser. Okay,
Yes.
and another thing is that when you pour the molten material in here in the pouring cup, then you cannot actually see what's happening inside.
Yes.
Cannot see that because of the smokes. Okay, because of the smoke of the boiling liquid, you cannot see how much cavity has been filled, and you can see through this way. You
Okay.
pour the molten material here through the pouring cup, and you observe the open riser, so that you can see whether the cavity is completely filled or not. So the open riser has two tasks. One is to take out the water, air, take out the air from the cavity, and the second one is to give the indication whether the cavity has been filled. Okay, and there is also sometimes a closed riser is also used. It has another purpose. The closed riser basically uh, reserves the liquid, that means the liquid metal, so that the material does not flow quickly. If you pour the molten metal here, then it will get a speed, a certain speed will be assigned to this material. Okay, the liquid, and then the liquid will flow very high at a very high speed, and very high speed will cause the breakage of these corners of the mold, or at very high speed, when just material is entering into the cavity, this edges this edges might break down, because those are just sand. Okay, they might break up. That is why there is a closed riser. That riser actually uh, slows down the material flow, so the material can flow very slowly into the cavity. And another task of this two riser is that when the material solidifies, as we already know that when you heat a metal part, it expands, right? Am I right? If
First, don't understand.
this is the initial part, if you heat it up, then its volume will expand, its volume will increase, and if you make it liquid, the volume will further increase. Why does it happen? It happens the because of the addition of heat, the atoms of this material, or molecules of this material, they get kinetic energy, and they get the distance between the atoms increases, and that is why the volume of the material increases, and in the case of liquid, it increases significantly. But when you solidify it, after the liquid is filled up with the cavity, when it solidifies, then there is a contraction, right? The volume will reduce, and if the volume reduced, then the cavity will not be the same. The final part will not be the same dimension as the dimension of the cavity, because there will be some empty spaces, the material will shrink. Okay, size will change. And to avoid that, to some extent, not the completely, to avoid this, so that the dimension can be maintained properly, uh, extra material is supplied from this riser and that riser. Both risers supplies the extra liquid into the cavity, and that happens before solidification, not after solidification. After solidification, material cannot flow, right? And how does it
sir.
happen before solidification? বলো, কেউ একজন কথা বলছিলা।
So I don't understand the last part of this area.
Last part means how the material gets shrinked.
Yes, sir. Yes, sir.
Okay, when you heat a metal, it expands. Do you agree with that?
Yes, sir. I agree.
Yes, sir.
Yes.
Yes, sir.
And if you heat it further, it expands more. If you make it liquid, the volume increases more, right?
Yes, sir.
If
Exactly,
you
sir.
Exactly, at the melting point temperature, the volume increases, but you cannot just pour the molten material at the melting point temperature, because if you pour it, it will be solidified instantly in here. Okay, and that's why you need to heat up the liquid metal further. If the melting point is 700 degrees Celsius, then you heat it like 800, 900 degrees Celsius, so that you can give it proper time, so that it can flow into the cavity before getting solidified. Then at the melting point temperature, if the volume is V1, okay, then above the melting point temperature, the volume will be larger, right?
Yes.
V2 will be larger. And after the completion of the filling up the cavity, when the cavity is completely filled up, then the temperature decrease from T2, that means the highest temperature T2 to T1, where the freezing occurs, right?
Yes, sir.
T1 is a constant. It holds for a long time, but temperature decreases from T2 to T1.
One.
Okay, and during this decrease in temperature, the volume also reduces. Volume comes from V2 to V1. And if the volume reduces, then the cavity size will not be maintained.
Sorry, sir.
Do you agree? The size of the cavity will also, the material cavity will be fixed. Size of the cavity will be fixed, but the material dimension will decrease, right?
Yes, sir. Yes, sir.
Sir, I have a question, sir.
Okay, go ahead.
Sir, as you said, uh, after the completion, before the solidification, we have to put the some extra materials through the riser to riser.
Yep.
So, sir, how could that be, sir? As you said, after the solidification, there will be a shrinkage.
Yeah.
So, before
No, not
solidification, how can
before.
I understand there is a
Before,
shrinkage?
yeah, before solidification there will be shrinkage. For example, I'll make it more clear. For example, you have a glass. Okay,
Yes, sir.
you need the solid dimension up to this. Okay,
Yes,
you need a solid part up to this. You pour the molten metal up to that point at a temperature T2. Okay, at a
yes, sir.
temperature T2, which is higher than the melting point temperature of that material. That means which is the freezing point temperature, right? Melting point and freezing point temperature are the same. Am I right?
Yes, sir.
Okay. So you put the molten material here at a temperature higher than the melting point temperature, and due to the decrease in temperature, the volume will reduce. Do you agree with that?
Yes, sir.
Yes, sir.
Then the volume will be reduced like here. Okay. But your purpose was to get this height, right? But due to
Yes,
the
sir.
decrease, you'll get this, and after reaching the melting point, you'll get this height. Okay.
Yes, sir.
And when it goes to the room temperature, TR, when it gets to the room temperature, the volume will further reduce. Okay. And that reduction occurs because the material is solid now. Material is solid at a temperature of melting point temperature. And when the temperature decreases to the room temperature, it will further decrease. Volume will further decrease, right? So this will be the final volume at room temperature. And now your question was, why should we provide extra material, right?
Sir, exactly, sir. Before solidification, why?
Before solidification. Uh, so this portion is reduction occurs after solidification. Okay,
Yes, sir.
and this reduction up to this point, this reduction occurs before solidification when material is liquid. Am I
Yes,
right?
sir.
And to compensate this one, we need to provide extra material, right?
Yes, sir.
So that is why that extra material is provided from the risers. Did you
Yes, sir. Thank you,
understand?
sir. Thank you,
We
sir.
cannot compensate the whole thing, but we can control this one, right? After solidification, we don't have any control over there. But before solidification, we have the control and we can do it.
Yes, sir.
Okay. Did you get it?
Yes, sir. Thank you, sir.
Okay. Okay. Any other question? No. Okay. Then we move forward. So next is the this is the solid. After solidification, this will be the solid part, and we also have some other things to discuss in here. That is the core. What is core, and what is chaplet? Okay. The core. When do we need a core? The main purpose of a core is to restrict the molten material flow into the cavity. Okay. The main purpose of the core is to restrict the flow of molten material into the cavity. For example, if this portion, this core was not there, then the whole portion from here to here, this would have been filled up with molten material. Am I right?
Yes, sir, it's true.
Okay. So if I want to have a hole into the material, for example, if I show a 2D view of a component, let's say I want to make this one, this is the component, then I don't need to put any core in here. The molten material will flow into the full whole empty region, whole cavity.
Yes, sir.
Then we can produce that. But if I want a hole in here, then how do we do that?
Okay.
We, because there is a restriction in the pattern making. If you because this hole has been made using a pattern, right? Using a pattern, we manufacture this hole. Because of the difficulty of producing pattern with a hole in here, we need to make the hole, the complete hole, and then we need to put a core in there. Okay, we need to make a pattern like this, and then we make the cavity similar to this. Cavity is also same. If this is a mold, okay, the cavity is also same, but I don't need to flow the molten material into this region. That's why I put a core in there, so that molten material does not go in that place.
This point, yes, sir.
Okay, then we get the final product.
It's fully depend on the design.
Depends on the design, definitely. If you need to produce a core, you can also do that using drilling, right? You take out the final part and then you drill a hole in there. But if you don't want to go to that, you want to make it at the first time, then you put a core in here so that material does not go into that place,
Yes, sir.
and that place will be empty. And then after solidification, you take out the core,
Yes, sir.
then you'll get the empty space in here. Did you understand the concept of core?
Yes, sir. Yes.
It will be more clear when we see the casting process. Okay, it will be more clear. Don't worry about that. And another thing is that chaplet. The main purpose of chaplet is to hold the core steady. Sometimes core can be longer. Okay, this core has a support of this much, right? This much sand is the support of this core. And when you pour the molten material into the cavity, this core might float. Is there any possibility like that? The core might float up? What do you think?
No, sir.
Why?
Sir, I can see there is a
Chaplet.
restriction
Yeah,
or tablet.
that's the restriction we
Yeah.
need to provide, so that the core does not displace because of the interaction with the metal. When you pour the molten metal, the core should not displace, and that is why we need to apply a chaplet. Now the question will be, if we place a chaplet like that, that also involves with the molten material, right?
Yes, sir. Has the main.
And how do we remove that chaplet? That would be a question, right?
Yes, sir.
Okay. And in that case, most of the cases, what happens is that the chaplet material is same as the molten material.
So
Okay, most of the cases the chaplet material is same as the molten material, and in other cases the chaplet material is very small. It just holds the core because there is not much force exerted by the molten material. It just need to stabilize the core. Okay, and that is why it's very small dimension, as well as made of same material, so that the material can interact with each other, and they also stick to the base material.
sir,
After that, you remove the core, and cores are usually made of sand. They can be broken easily. Okay,
sir, from the diagram, I think the chaplet acts as a barrier, sir. But this looking like a barrier. That we if you use that, the air cannot out from the open riser.
oh no, it's 2D. You're seeing the 2D view of this, right? Because there are enough space. It's a 2D view. There is enough space around it.
Oh, okay, sir. Okay,
It's a
sir.
two-dimensional view. That's why you see the blockage, right? The material cannot flow in this way, but it's 3D, so material will flow. Okay, around this cavity, around this chaplet, or around the core. Okay.
Thank you, sir.
Okay. Do you have any question? I think this will be further more clarification you'll get once you move to the other sections of the casting. Then by the time you'll be able to understand all of this. But since this is the first class, you are just being familiarized with the terms, so it will be really hard for you to understand. But by the time we move forward, then it will be more and more clear, because we will be seeing this kind of different kind of molds throughout the casting lecture. Okay. All right, so moving forward, oh, I have put animations. Okay, so the 10 more casting procedure. How do we conduct a casting? Okay, how do we make a part using the sand casting? Okay, this is the uh, portion of the lecture where you will understand that a lot of things will be uh, clear from this casting procedure. At the first step, you need a plane surface. Okay, a plane. Oh, sorry. First, what do you need first for manufacturing a product using casting? You need a pattern.
So we need a pattern.
You need a pattern. Okay, this, the the product that you want to make, you need a replica of that product. Okay, so once you have the replica, that is called pattern. And the problem is that the pattern should have a parting line. If the pattern is flat, then it does not need a parting line. But if the pattern is irregular shape, then you need to split it up into two parts. Okay, you need to split it up through the parting line, so that you put the first half on this side and second half on the other side. And why do you need that? You'll get it, you'll understand it very soon. Okay, so you have a pattern like this. Okay, you have a pattern like this. You have two part of the pattern split on the parting line. According to the parting line, the pattern is split into two half. Okay, now the first half, the bottom half, you have a flat sided half pattern placed on a flat surface. Place the pattern on the flat surface. I'll not go into the detail, I'll just tell you the overview of the casting process. There are some other steps. Okay, I'll go to that when I repeat the procedure. Okay, so first I just want to point out the major things. The first, you have a flat plate or flat surface or floor, whatever you can find. It has to be flat. Okay, you put that first half pattern in there, and then you put sand into the sorry, you put the drag in place upside down. The drag upside, this is the upside of the drag. Okay, you need to put upside down. Okay, put the drag upside down, and then you put the first half of the pattern. Okay, and then you put the sand. You do the ramming, that means packing the sand, and then finally stickling off, so that the surface become straight. Okay, you take the extra sands out to make the surface straight, and then you make it upside down again. That means this clump was at the bottom, now this clump will be at the top, and the first half is complete. Okay, then in the second half, you place the second cope, or that means the top part of the flux. Okay, you put the cope in place, you do the clamping. Okay, you do the clamping on the both side, and then you place the second half of the pattern in place, so that you can get the complete cavity. Okay, you put the first half on the drag, and then you take it upside down, and then you put the second half. And how do you put the second half in position? There will be some dual pins in here. Okay, there will be some at least 2 pins in here, so that the pattern, both patterns can be aligned in place, okay, properly. Once the second part is placed, then you need to have a solid part that is called sprue pin, through where you don't want the sands to go. You want this place to be empty. Sands should not go in this place. So you put a sprue pin, you put a riser pin through which the material, you will see the material filling up. Okay, then you put another solid part in here, and then once you put the sprue pin and riser pin in position, and also the pattern, other half of the pattern in position, then you fill it up with the sand and pack it properly, ram it properly and pack it properly. Then another thing is that on the pouring basin, that means where we said like a pouring cup, you make the pouring cup by removing the sand. Also at the on the riser side, you can make the pouring a funnel like structure. Okay, and then you take out the pouring pin, sorry, sprue pin and riser pin. You take both of them out, and before that you need to make the surface really flat. Okay, surface has to be really flat by the same method like stickling off. Okay, surface is flat. You take out the sprue pin, and also you take out the riser pin, and then you again unclamp it. The clamping, you remove the clamps, and then you take the drag out and put it beside the uh, uh, sorry, take the cope out and put it upside down. Okay, again, then from the drag, you take off the first half of the pattern. The first half of the pattern, you take the first half of the pattern out. Okay, and then from the cope side, you take the pattern out. You take the whole pattern out actually. Okay, and then you put them together again. Before putting them together, can you see any place where so that the material can flow into the cavity? There is no place, right? This empty space is created using the sprue pin. Okay, and this empty space is created using the riser pin, but there is no connection between the between those two, because the sand is filled up. Sand is filled up in this place. Sand is filled up in this place. There is no connection. So once you separate the drag and cope, then you need to take out this extra sands. You need to take out the extra sands from here, so that cavity is connected to the riser, and cavity is also connected to the pouring sprue. Okay, once it is connected on the both side, then you put the drag and cope together again. You clamp it up. Okay, you clamp it up, and then you put the molten material into through the pouring basin, and then the material gets filled up. The cavity gets filled up, and you can see the material coming out through the riser, so that the cavity is filled up, and then you allow some time for solidification, and then you take the part out. Okay. Okay, you might have a question like, why these white regions in here? In this case, the riser does not serve the completely to remove the air, because once the material is filled up to that position, the riser gets blocked. That air is trapped in this region. How do we remove that trap? We need to use vents. These are called vent. Using a very thin steel rod, we produce vent. Once this is done, on this step, on the third step, we need to produce some vent using wires, steel wire. We need to produce some vents, so that the extra air trapped in here during pouring of molten metal should get out of this way. Okay, all right, do you have any question? Is it very complicated?
It's easy, sir.
Easy or very complicated?
Seems easy.
easy. But another thing is that you might also think that there is empty spaces in here, there is empty spaces in here, this sand might fall down, right? Who has this question in mind? Anybody? Nobody? That's nice. If you don't have any question regarding this, because it's 3D, okay? These holes are just if you look from the top, if you look from the top of the mold, this hole will be here, this hole will be here, a small tiny hole, a small tiny hole, a small tiny hole, and that one will be larger, okay? And all around it are the sands, okay? Sands are filled on all around it, so that there is no possibility that this one might break down, okay? So in my previous year, when I conducted the class for leather engineering, I have encountered this question. That's why I just clarified it. It is a three-dimensional structure, and sands are really packed. You might have done some, if you go to the sea beach, you might have done uh, uh, some castle making, right? It's a similar process. It does not break so easily, okay? Sands are packed all around so that it does not penetrate into the system. So one more time, I will just repeat the process, okay, so that it becomes really clear to you. Firstly, we need a flat plate and we need a pattern which is divided into two parts along the parting line, okay? And that pattern, first half of the pattern is placed on the flat plate, and then you pour the sand and pack it. Make the surface flat, okay? Make the surface flat and make it upside down. Once it is upside down, you place the cope in place and clamp it properly. Once the clamping is done, you put the other half of the pattern using the dowel pin in position, and then you put the sprue pin, which is a solid material, and riser pin, which is also a solid material, so that sand does not go to that place, okay? Then you put the sand in there, and then you fill it up the whole space using the sand and make the surface flat, and then create the pouring basin and the riser basin, okay? And then you do the venting using the wire. You do the venting so that air can get out of the cavity, okay? And then once everything these things are done, then you again unclamp it to remove the pattern. Pattern is a solid material, it is made of wood or plastic, okay? Then you remove the pattern, you remove the pattern from the drag, okay? You remove the pattern from the cope, and then you cut the space like runner, okay? You make the space so that molten material can flow into the cavity, or molten material can get out of the cavity through the riser, okay? You need to make that space, and then you again put them together like this, and then you pour the molten material into the pouring basin, and it goes through the runner to the gate and into the cavity, and from the cavity it gets out of the riser, and extra air trapped on the top of the cavity gets out through the vents. Sometimes if the vent is very large, then molten material can also go through the vents. Once the solidification is complete, you allow some time for solidification. Once the solidification is complete, then you break the mold. Because it is a sand mold, you can break it very easily. Just unclamp it and remove the sands, and then you'll get solid part including all of this, okay? You'll get a solid part including this one, this one, this one, this one, and that one, okay? Everything will be attached with the part. Then you do the clearing and finishing. For clearing, you cut it off in here, you cut this one, you cut this one, cut this one, and that one. You take them off, and then you'll get this will be your final part. And you can do the finishing on the surface so that you can get very shiny look, okay? All right, do you have any question?
No, sir.
All right, so moving forward, for the pattern, there are two types of patterns in One is removable pattern, that the pattern that we have talked about in the previous slide, that is called removable. You just remove the pattern, you separate the drag and cope, and then you remove the pattern. That is called removable pattern. But there is another type which is called disposable pattern. In the case of disposable pattern, you don't remove the pattern. Okay, you make the mold. Let me clear it. You make the mold, okay, and then in the mold is the pattern is made of the wax, or we can say like paraffin wax, okay, or any volatile material that can be evaporated once we heat it up, okay, or we can use higher temperature to melt it. Okay, wax can be melted at 40-50 degrees Celsius temperature, and the pattern consists of, at the same time, the pattern also consists of the riser pin and uh, screw pin with the runner. Everything is made of wax. Let's say wax. Okay, everything is made of wax. You make all other procedures are the same. You don't need to split the pattern. You don't need to separate the pattern. Pattern is solid part. Along with all of these are solid part. You place them in the position, and then you fill up the whole flux. You pack it properly, and then you make it upside down. That means this, if this is the top side, you make it upside down, and then apply heating. Okay, apply heating from both side, or any other side, from all side you apply heating. Once you heat it up, then the material, since the material is made of wax, at 60-70 degrees Celsius temperature, this material gets out through the pouring basin and through the riser. Once the material gets out through the pouring basin and through the riser, then you will get the cavity. Okay, and this sort of patterns are called disposable pattern. You can use just once. But in the case of solid patterns or wood patterns, you can this is also solid pattern, but in the case of wood or metallic or plastic patterns, you cannot use it. You can use it again and again to manufacture a lot of parts. But in the case of disposable patterns, you can't do that. Once the mold is prepared, then the pattern is gone, because of the heating, pattern becomes liquid, and it gets out of the mold, leaving the cavity behind. Okay, so that is called the disposable pattern. And for did you understand that disposable pattern? Any question in here?
No, sir.
All right, then for removable patterns, there are some advantages. It can be reused. You can reuse the pattern. Okay, can be used in machine molding. That means automatic molding method can be used with the removable patterns. It's very easy. The cavity produced can be inspected. The cavity that has been produced, you take out you separate the drag and cope, and then you inspect the cavity whether there is any fault. But in the case of removable pattern, you don't have that flexibility. Okay, and easy to handle using the removable pattern, because it does not break so easily. And disposable patterns, those patterns are basically made of wax or very low strength material. That is why they can break so easily. So it's very difficult to handle. And the disadvantages of removable pattern includes time required more, because you need to take it out and place it again, and you need to cut the gates and pouring basins and all other things. But in the case of removable disposable pattern, you don't need to do that. The finishing is not good. More metal is needed. If you compare between the disposable pattern and removable pattern, the more metal is needed for casting. In the case of removable pattern, the complex pattern with loose pieces is difficult to handle. If there is a complex pattern and a lot of parts involved with a single pattern, then it is very difficult to remove the pattern to produce the cavity. Okay, so that is why it is very hard for to handle the removable pattern. In the case of disposable pattern, advantages includes the time required less metal needed, Mold making is very simple. You just make the mold and heat it up to create the cavity, and the finishing is also good because the wax pattern that you produce or any volatile material pattern that you produce are very you can produce a very fine surface, okay, very finished surface, and that gives you the very finished product of casting. And the disadvantages are not reusable. You cannot use it again and again. The cavity produced cannot be inspected, that I have already talked about. The automation is very kind of difficult, and the patterns are difficult to handle because they are fragile. They can break very easily. Okay, so that's it. Do you have any question for today, the whole lecture?
Sir, is that okay to use the volatile materials for casting?
Yep, definitely.
So, sir,
You
because
can.
sir, it might trigger a lot of sir calamities for our environment.
Yep, that's a different concern. As a engineer or environmentalist, you might definitely consider that not using the volatile material. But one thing I can tell you, like you can use like dry ice to make the pattern. Okay,
Okay, sir.
something
Thank
like
you,
that.
sir.
Also, the carbon dioxide is harmful to the environment. So you have to be really aware of that. Okay.
Yes, sir.
Okay. Any other question or concern? So if not, then I will conclude here, and in the next class we'll study the pattern allowances and the core. We'll study the in details how the pattern allowances are given, and the core, how do you place the core, and what is the benefit of the core, what are the materials of the core, and what are the properties that a core should have to make a proper casting. Okay, and the pattern allowances, how do we control the dimension of the pattern. Okay, because there are a lot of things need to be considered for to manufacture the pattern, because the final product of a casting depends on the pattern, the replica that you are using. Okay, if the replica is faulty, your final product will be faulty. All right, so